Okay, hello physical science. It's Mr. B. We're going to finish up section 2, kind of wrap up Newton's first and second laws, and what we're going to do to wrap up this is to kind of clear up a misconception of two words that I think get used interchangeably quite often, but they are in fact quite different. So, and those two words, to jump right into it here, are weight and mass. So I've used both of these words kind of throughout explaining Newton's first and second law, and so at times, I think they get used interchangeably when they're really not the same thing. So our big difference, and actually kind of similarities too between these, are going to be that mass is a measure of the inertia of the object. So that's, again, it's a tendency to resist motion. So how much you want to resist motion kind of will determine how much mass you have. And weight is the measure of the force of gravity acting on an object. So there's two very different definitions right there, but they are going to be related to one another. Again, we can't really know one without knowing the other, so you need to make sure you write both of those down. So mass is how that's going to resist a change in motion, and weight is the measure of the force of gravity that's acting on the object. And so mass and weight are related, but they are not the same. So it's technically not correct when you use them interchangeably. So mass is, kind of for another definition, is the measure of the amount of material an object contains. So how much stuff you actually have, to put it simply, is what your mass is. So that's kind of, again, the simple definition. How much stuff there actually is present at any time is how much mass there is. And then for weight, it's the force of gravity acting on an object, and weight is the product of mass and acceleration due to gravity. So weight actually includes mass and gravity together, and so that's where we're going to get a little equation that W equals mg is a different form of Newton's second law of force equals mass times acceleration. So weight equals mass times acceleration due to gravity is another form of Newton's second law of motion. So, and the value of g in the formula is always going to be 9.8 meters per second squared. So these problems are always going to be pretty simple when we're thinking of weight and mass, because we're always going to know that the g, the acceleration due to gravity, is 9.8 meters per second squared. So this is almost a little bit of a simpler version, I think, because we always kind of know what one of these answers is going to be. And so a quick example is, if an astronaut has a mass of 112 kilograms, what is his weight on Earth, where the acceleration due to gravity is 9.8 meters per second squared? So we just do weight equals mass times acceleration, 112 kilograms times 9.8 meters per second squared. And then we get this kilograms per meters per second squared, and we know that that is in Newton. So then it's 1,100 newtons. So on the moon, the acceleration due to gravity is only about 1/6 of that on Earth. So therefore, the astronaut only weighs about 1/6 as much on the moon as it does on Earth, and the mass of the astronaut is the same on moon and on the Earth. So that is kind of a big, the big difference, I think, between weight and mass is right there. On Earth and the moon, they weigh differently because the force of gravity is much less than it is on the moon than it is on Earth. So weight is different if I was standing on the moon. However, the mass is identical because I'm not changing how much space I'm actually taking up. So that's my biggest way, I think, to easily remember the difference between weight and mass, is to think about the moon. There's less gravity on the moon, so therefore weight is mass and gravity, so my weight is going to be less if I'm on the moon, whereas my mass, that can never change unless there's some serious problems, because it is just how much space I actually take up. And to look at our picture, the astronaut on the Earth, it has a mass of 88 kilograms of a weight of 863 newtons, and then on the moon, its mass is identical, 88.0 kilograms. But then again, since the acceleration due to gravity is about 1/6 on the moon that it is on Earth, now our weight drops all the way down to 141 newtons for this astronaut. So big takeaway message, different from weight and mass. Mass is how much space you take up. Again, your tendency to resist inertia, or how much inertia you have, your tendency to resist motion. and then your weight is your mass times the acceleration due to gravity. So again, we will go over this more in class. We'll work with some sample problems and things like that. So just be clear. Hopefully the biggest takeaway message here, weight and mass are different, and hopefully you can identify what the difference is between those two. So that's going to be it for section 2. Let me know if you have any questions.